In today's lecture, we'll finally start looking at the zeros of polynomial functions from an algebra side. Now remember, our main goal is to completely factor every polynomial and find its zeros, because finding the zeros of a polynomial allows us to sketch the graph and really start to look at the properties of polynomials as a whole. And the way that we'll be finding our zeros is with the fundamental theorem of algebra. And it's so important that I'm going to highlight it as well. Now what the fundamental theorem of algebra says is that every polynomial of degree n with n greater than 0 has at least one zero in the complex numbers. So we can always find a zero if we're working with complex numbers. And moreover, if we count repeat zeros individually, then every polynomial of degree n has exactly n zeros. So we should always be breaking this down into n different linear factors. So to understand this a little bit better, let's look at an example. We've seen the function negative 2x to the fourth plus 2x squared before, and we factored it down to be 2x squared times x plus 1 times x minus 1. And then we wrote it a little bit differently, to be 2 times x minus 0 squared times x plus 1 times x minus 1. Or maybe we even go to the extreme and we write this as 2 times x minus 0 times x minus 0 times x plus 1 times x minus 1. And now we can see our four factors. If we count our x minus 0 squared term here as two zeros, then we'll have exactly 4 to look at. It's just two of them are repeated twice and they change the graph a little bit. We can restate this as the linear factorization theorem, which says that if f of x is a polynomial of degree n, then f of x has precisely n linear factors. Or in other words, we can write f of x as a bunch of zeros all multiplied by each other, like we did above. But now the c1, the c2, and the cn are all complex numbers instead of real numbers. What this means is that all polynomials can be completely factored by just adding in the square root of negative 1 and looking at our complex numbers. So let's take a look at an example here, and let's factor f of x is equal to x cubed plus 4x and find where these zeros are. So first of all, let's pull out an x from both terms and rewrite this as x times x squared plus 4. Now remember, if we want to factor, this is the same thing as setting it equal to 0 and solving each piece. So this is really x is equal to 0, which becomes a linear factor x minus 0. And x squared plus 4 is equal to 0, which becomes x squared is equal to negative 4. Take the square root of both sides, and we get x is equal to plus or minus the square root of 4 times I, or x is equal to 2i, and x is equal to minus 2i, which gives us our linear factors, x minus 2i here, and x minus negative 2i, which is the same thing as saying x plus 2i. Now that we found our zeros, we can rewrite x cubed plus 4x as x minus 0 times x minus 2i times x plus 2i. And we have completely factored our polynomial into the three linear terms that we should have. Let's do one more here. All right, we're just going to factor x squared minus 6x plus 9. This one's not too bad. If we use our rules, we're looking for two numbers that multiply to be 9 and add add to be negative 6, and they're going to be negative 3 and negative 3. So this becomes x squared minus 3x plus 9. And we see the equation hasn't changed. So now we group them up. X squared minus 3x. Remember, if we have a minus here, when we factor it out, it changes everything. So minus 3x minus 9. When we put the negative back in, it flips everything back, and we'll get minus 3x plus 9. But for now, factoring like this makes it easier. So we'll pull an x out of the first term. And we have x times x minus 3 times x minus 3. And after grouping, we have x minus 3 times x minus 3. Even though we only have one 0 at x is equal to 3, we have two linear factors. They're just repeated. So remember that in order to find our entire linear factors, we need to look at our repeated roots individually. So here we have two copies of x minus 3 to have a total of 2. Now how do we find these zeros? Well, in general, finding zeros takes quite a lot of work. But we'll look at 3 techniques to help us really narrow this down and find the zeros of a polynomial. And the first one we'll look at is the rational root test. And this is the most powerful. The other two will just make the rational root test more accurate. So since this is so important, why don't we highlight this one too? What the rational root test says is that if the polynomial f of x is equal to an times x to the n plus a minus 1 times x to the n minus 1 plus blah 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 plus a1x plus a0 has integer coefficients, so the an and the an minus 1 are all integers, then every rational zero of f has the form p over q, where p and q have no common factors, meaning we can't simplify them anymore, and p is a factor of a0, which means a0 divided by p is an integer, and q is a factor of an. So the leading coefficient goes on bottom, and the last coefficient goes on top. With this, we can start narrowing down which zeros to look at, and start plugging them in and using synthetic division to see if we're right. So let's use this in practice, and let's see if we can find all rational zeros of f of x is equal to x cubed minus 5x squared plus 2x minus 8. So let's get started. We're looking for zeros of the form p over q, where p divides the last number, 8, here. Why don't we highlight that in blue? And q divides the first number, which we'll highlight in green, which is just an invisible 1 right here. Remember, if there's no number in front, it's always a 1. Okay, so what numbers divide 8? Well, 1 divides 8, and we have plus or minus 1. Plus or minus 2 divide 8. 8 divided by 2 is 4. 8 divided by negative 2 is negative 4. 4 divides 8, and 8 divides 8. So for every positive divisor, we pick up a negative 1, and we just count up and see how many different times can we divide 8 by a number and still get an integer. The numbers that divide 1 are easier. The only number that divides 1 are positive 1 and negative 1. So this means that our potential zeros are plus or minus 8 divided by plus or minus 1, plus or minus 4 divided by plus or minus 1, plus or minus 2 divided by plus or minus 1, and plus or minus 1 divided by plus or minus 1. So we take these numbers and we put them on top here. And in general, we take the other numbers here and we put them on bottom. But since it was plus or minus 1, things didn't get too complicated. So let's try x is equal to 4. Or in other words, let's try factoring out the linear term x minus 4. Since we have something simple, we'll just use synthetic division here. So 4 goes on the outside. And then we pick up the coefficients of our polynomial. 1, negative 5, 2, 8. And we use our pattern. 1 goes outside. 1 times 4 is 4. Negative 5 plus 4 is 1. Negative 1. Negative 1 times negative 4 is negative 4. 2 plus negative 4 is negative 2. Negative 2 times 4 is negative 8. And 8 plus negative 8 is 0. So it worked. X minus 4 is a factor that divides. And the remaining factor is x squared minus x minus 2. Remember, that's because these numbers here, which we'll highlight in purple, 1, negative 1, and negative 2, are exactly these numbers outside of the box here. Once we're at x minus 4 times x squared minus x minus 2, we can just factor the quadratic term and get it to be x minus 4 times x minus 2 times x plus 1. And then our zeros are x equals 4, x equals 2, and x equals negative 1. So these are the points on the graph that are our x-intercepts, or our zeros. Now this is a very helpful technique, but in general, it can still be quite messy. Let's try to find all rational zeros of the polynomial f of x is equal to negative 10x cubed plus 15x squared plus 16x minus 12. All right, so what are factors of negative 12, which is our a0 term? Well, we have plus or minus 12, plus or minus 6, plus or minus 4, plus or minus 3, plus or minus 2, and plus or minus 1. These are all the numbers that divide negative 12 and end up with an integer. On the other hand, we have factors of negative 10, which is equal to our a sub n term. And these are plus or minus 10, plus or minus 5, plus or minus 2, and plus or minus 1. Combining all of these, this means our potential zeros are all the divisors of negative 12, divided by all the divisors of negative 10. So in order to see where our zeros are, we would have to pick a number on top, maybe check out plus 6, pick a number on bottom, how about plus 5, do synthetic division and see if it's a 0. What this means is that we have 32 possible combinations by picking a number on top and a number on bottom, and we have to check all of them until we come up with a 0. And that's pretty terrible. So we have a nice technique right now, but we need to refine it a little bit more and develop some more techniques to try to narrow this down. All right. So the last thing we'll talk about in this lecture will be ways that we can factor a polynomial with complex numbers. So first of all, remember that every polynomial of degree n greater than zeros with real coefficients can now be written as a product of linear and quadratic factors, but now our coefficients are in the real numbers. Sometimes this is simpler. If we don't want to deal with complex numbers, instead of just doing linear factors, we can add in these quadratic factors and make our life a little bit easier. However, the quadratic factors are a little bit strange. All of the zeros in our quadratic factors are not real numbers. So any complex zero we have, we can suck up into a quadratic factor and make our life a little bit easier. However, we can note a nice thing here. If we do have a complex zero, then it will occur in a conjugate pair. All complex zeros of a polynomial occur in conjugate pairs. And what that really means is that if we have a zero, a plus bi, then the complex conjugate a minus bi is also a zero. So if we find one complex zero, we've actually found another one right away, just the complex conjugate. So let's put this into practice. Let's find all zeros of f of x is equal to x to the fourth minus 3x cubed plus 6x squared plus 2x minus 60, knowing that 1 plus 3i is a zero of f of x. Okay, so what does this mean? This means that x minus 1 plus 3i is a zero, or a factor of our polynomial. So we can use synthetic division, and 1 plus 3i is our zero, and simplify the polynomial. But honestly, that sounds a little bit hard. We haven't done synthetic division with complex numbers before. So we're going to make our life a little bit easier, and use the fact that we also know x times, or x minus, the complex conjugate, 1 minus 3i, is also a factor. And instead we will combine these and use long division. Okay. So we have x minus 1 plus 3i times x minus 1 minus 3i. And if we multiply these together, we should still have a factor of our polynomial. And these will be x squared minus x plus 3ix minus 3i plus, left off a term there. So let's see, let's go a little more slowly here. X squared is x times x. Then we do outer, so x times minus 1 minus 3i. So that's where we pick up the second term. Why don't we write it out very carefully here? So this is plus negative x plus 3ix. Now we'll do the inner terms, which is minus 1 plus 3i times x, which becomes minus x minus 3ix. And then finally we have the last two terms, which is 1 minus 3i times 1 plus 3i. Okay, we have our four terms. First, outer, inner, last. And now we can simplify these down. This is x squared minus x plus 3ix minus x minus 3ix. And for the last term, we have a number times its complex conjugate. So this is plus 1 squared plus 3 squared, just from our formula. And we'll notice that two terms cancel out here, the plus 3ix and the minus 3ix. So this actually becomes x squared minus 2x plus 10. we've changed from two complex factors into one real quadratic equation. And now that we have this, we'll take our real quadratic equation and we'll divide our original polynomial by it with long division to come up with something simpler. So our two linear complex solutions became one real quadratic that we can divide by. And we'll divide the original polynomial in here. So if we remember how to do this, we ask ourselves, what is x to the fourth divided by x squared? And the answer is x squared. So we get minus x to the fourth minus 2x cubed plus 10x squared. And this simplifies down to minus x cubed minus 4x squared plus 2x minus 60. All right, now again we ask ourselves, what is negative x cubed divided by x squared? And that's going to be minus x. And when we multiply negative x in here, we get minus x cubed plus 2x squared minus 10x. We simplify this and we get 0 minus 6x squared plus 12x minus 60. And finally, what is negative 6x squared divided by x squared? Well, that'll be minus 6. And we carry that through and we'll get minus negative 6x squared plus 12x minus 60. And now everything cancels out and we have our divisor. This is x squared minus 2x plus 10, our complex zeros, times whatever's on top, which is x squared minus x minus 6. And then all we have to do is either factor our last quadratic here, or use the quadratic equation and find our remaining two zeros. However, we can factor this one pretty simply. This will just be x minus 3, x plus 2, and we picked up our remaining two zeros right here. So if we write out our zeros, we had x is equal to 1 plus 3i, which was given, x is equal to 1 minus 3i, which was the complex conjugate, and then factoring the remaining quadratic gave us x is equal to 3 is a 0, and x is equal to negative 2 is our fourth zero. And this is our form. This is as simple as we can break it up so that we only have real numbers and we don't have any quadratic numbers. All right, so in the next lecture, we'll look at a couple more techniques, and that will make it so we can find these zeros easier so that we don't need to be given them right off the bat.